Hi folks, today we're looking at the derivatives of all 6 trig functions. And to get into it, I guess we'll take a look at the last question from the homework from the last lesson, which was to find the derivative of sine x over cos x. So from the homework question, we learned that the derivative of tan x is secant squared x. And here's how we did it. We said tan x, here was the question we were given, sine x over cos x. If we want to differentiate that, well, we just take derivative of the top and derivative of the bottom, and use our quotient rule. So u prime v minus u v prime all over v squared. That gives us cos squared x plus sine squared x. And that might look familiar to you. Sine squared plus cos squared is just 1. So the derivative's 1 over cos squared x. And we can rewrite that as secant squared x. 1 over cosine is secant, so 1 over cos squared is going to be secant squared. In a similar way, we can find the derivative of the other 3 trig ratios. And we'll do one of those together and then just catalog all the rest. In this question, we'll find the derivative of cosecant x. So we can think of cosecant as 1 over sine x. And that means we're going to have to use quotient rule. Derivative of 1 is 0. Derivative of sine is cosine. Now we're ready to get going with the quotient rule. So we get g prime of x is u prime, so that's 0, v, which is sine x, minus u, which is 1, v prime, which is cos x, all over sine of x all squared. And it works out pretty nicely. We're going to have 0 minus cos x, so negative cos x. I'm going to leave this as sine x all squared, though we could write it as sine squared x. And from there, we've got a bunch of different ways we can simplify this. So one way that we could rewrite this is as negative cos x over sine squared x. And that's a perfectly okay answer for this. The common way to notate this is to try and avoid fractions and try and avoid powers within our trig functions. So here's another way that we could re-express this. I could split it apart. I could say g prime is, I got a 1 over sine x times, and maybe I'll keep the negative with this, times cos x over sine x. It's equivalent to the last step. I've just split things apart. Why? I guess because I can. Maybe it'll turn into something nice at the end. So 1 over sine x is cosecant x, and cosine over sine x is cotangent x. These are both expressions for the derivative of cosecant x, but we tend to prefer this one over here. By a similar method, we could find the derivatives of secant and cotangent. We're just going to list them in the next table, and in the homework you'll have an opportunity to do the missing ones. So here's our full list of trig derivatives. Sine goes to cosine, cosine goes to negative sine, tan goes to secant squared, cotangent goes to negative cosecant squared, secant goes to secant x, tan x in a similar way that we showed with cosecant. Cosecant x, there's the one we just found, and just so we have them, there are product and quotient rules. Since everything in trig can be boiled down to sine and cosine, really it's most important to know how sine and cosine behave when we differentiate. And since everything can be boiled down to sine and cosine, there are often a lot of different ways that you can represent an answer. So we'll start to see that as we do some derivatives involving more of these trig functions. And let's start with this one here. We've got secant x over 3x squared. So clearly this is going to be a quotient rule. I'm going to have to figure out what the derivative of secant x is, and I've got it right here. It's secant x tan x It's a bit of a mess, but we just roll with it. 3x squared, no big deal. That becomes 6x. Now we're ready to differentiate. So it's going to be u prime, which is secant x tan x, by v, which is 3x squared, minus u, which is secant x, by v prime, which is 6x, all over v squared. And I'm putting everything in brackets to be paranoid and make sure I know what's being multiplied together. Let's see what happens when we multiply them out. So I'll get 3x squared secant x tan x minus 6x secant x. Usually we don't expand the bottom, but when it's just a monomial, it may be worth doing because there may be opportunities to simplify. So 3 squared is 9, x squared squared is x to the 4. There we go. That's a fine answer for this. Now, if we want to simplify a rational expression, we need to factor and then see what we can cross out. So let's take a look at the top. What's common? Well, we really just have two terms, one with a 3, one with a 6. So numerically, 3 is a common factor. One has an x squared, one has an x, so 3x is a common factor. And they both have secant x in them, so that's a common factor as well. I can pull all of that out, and when I do that, what am I left with? Well, if I take 3x out of 3x squared, I'm left with an x. If I take secant x out of secant x tan x, I'm left with tan x. And then in this last one, if I take 3x out of this, remember that would mean that I'm dividing 3x out of 6x, so I'd have 2. If I take the secant x out, well, that's all I'm left with. So there's another good-looking answer to this question. This one was correct. This is correct. At this point, though, you can do some real cancellation. So if you did some canceling before, that might have been pretty dicey. Right now, it's all factored out. So I'll get my red canceling pen out. 3 over 9. And really, it's reducing fractions. We shouldn't be using the word canceling necessarily. X over x to the 4, that's going to make this an x to the 3. So a way that I can write this is as secant x by x tan x minus 2 all over 3x cubed. If we can easily reduce, we probably should. If we can't, we can just leave it as is. And this is the prettiest form that we've got so far. But those other ones were okay as well. They were correct. Now, if for some reason you wanted to get really fancy and say, I don't want this secant x here, I want to call that a cos x on the bottom, I guess you could do that as well. So I'm running out of space here. But as another optional answer, we could call this x tan x minus 2 all over 3x cubed. And secant x on top is the same as a cos x on bottom. How many right answers do you need? You need 1. Okay, so as long as you've got 1 that's correct, you're doing well. But I want to show you that there are a bunch of different ways that you can run into these answers. And you should know whether yours is equivalent. So you might have a right answer even if it doesn't look like, say, the answer key or the back of the book. We'll do a couple more like this. So here's one with some other sneaky business in it. Number 1, you might notice that it has a radical, so we're probably going to have to re-express that. But the other thing that we might sometimes miss is the fact that this is root x times sine x. So this is a product rule. There are two x's without a plus or minus between them. I'll rewrite it in exponential form. And then I'll set it up for that product rule. So really I'm thinking my quote u is x to the 1/2, which means that my u prime is 1/2 x. Power goes down by 1, so x to the negative 1/2. My v, or my second term, is sine x. So its derivative, v prime, is going to be cos x. And that's in the table, and it's also in the wheel of trig. Now we can differentiate. So I've got u prime v, so that's 1/2 x to the negative 1/2 times v, which is sine x. And I could put these in brackets if I want, just to be sure that it's multiplication, plus u, which is x to the 1/2, times v prime, which is cos x. Full marks. That's the answer. Is it the prettiest form of the answer? Maybe not. You can optionally simplify it, and the answer in the back of the book will probably look a little nicer than this. So optionally, what are some things we can do? Well, I think we can say that we don't love the fractional exponents. So this is really a square root that lives on the bottom, and this is really a 2 that lives on the bottom. So this whole first part here is sine x over 2 root x. The other part, I can write it as root x cos x. And I think it would be fair to say that that looks a little bit prettier. And some people may have already memorized what the derivative of x to the half is. It always turns out to be 1 over 2 root x, so you could jump maybe straight here. Maybe you're looking at that and you'd like to make it into a single expression with a common denominator. Sure, you can do that. So let me just rewrite what we've got here. Really, I've got root x cos x over 1. If I want a common denominator, maybe I'd times the top and bottom of this by 2 root x. And what would that give me? Well, that would give me dy by dx is sine x plus, let's check this out, root x by 2 root x. So that's going to be 2 root of x squared, or just 2x, cos x, and that would be with that common denominator of 2 root x. Let me write that a little nicer, 2 root x. These are all fine answers. Which one's the best kind of depends on what you're going to do next, but there are a lot of ways to express these answers. We'll do one more that looks at another one that has a bunch of different possible ways of expressing the answer. All right, we'll take a look at one last sneaky one here. So we've got 1 plus cosecant x times cosecant x. Now your first inclination might be just multiply them all out and then differentiate each little bit. But notice that if we did that, we'd get a cosecant squared, and we don't have something easy to deal with in terms of cosecant squared over here. Yes, you could use a product rule for cosecant squared, but that's really not a whole lot slicker than using the product rule right here. So we have two functions of x multiplied together. Let's call this first one our u, which means that our u prime is going to be the derivative of cosecant x, which is negative cosecant x cotangent x. Cosecant x is going to be our v. Maybe I'll just color code this just so we're clear that this is a different function or piece of the function that we're taking the derivative of. But it's going to have the same little derivative. Okay. Negative cosecant x times cotangent x. Now we're ready for the product rule. So the product rule is u prime v. So u prime, I got a lot of terms here. I'll use some brackets. Times v plus u by v prime. Yeesh. There's a lot happening here. Let's multiply out and see what we get if we can make this look a little nicer. So in this first term we have a cosecant by a cosecant. That'll make a cosecant squared. So I'll have negative cosecant squared x by cotangent x. Over here I'm going to have to distribute. So 1 times this whole mess is going to be negative cosecant x cotangent x. And then if I do the other piece of the distribution, I'll have negative, this will be cosecant squared x, cotangent x. So we've got some kind of sneaky algebra happening here, but really it's just distributive property. Now take a look at what we've got right now. We have like terms. There's a negative cosecant squared x cotangent x here. There's another one here. Put them together, you've got 2 of them. And we're done. Or potentially we're done. Okay, so great. What can we do that's different from this? Well, you might notice that there are common factors here. So you might want to take out cosecant x, cotangent x. You also might want to take out the negative so that we have positive in the bracket. Totally up to you. So a thing we can do is that we could take out negative cosecant x, cotangent x. What's that going to leave us with? It'll leave us with 2 cosecant x plus, it'll all be gone from this one, so plus 1. There's a nicer way that we can show it. Now from here, there are other things that we could do. We could go to sine and cosine, and maybe it'll look pretty from there. I'll do a bunch of that, and maybe we'll talk about the process at the end of it. I'm going to need to erase some of this, though, probably as I go, because there's a lot that's going to happen. Okay, so there are some things that we could do. Phew. We could go to sine and cosine, and once I did that, I collected some terms, I multiplied in. This is kind of nice over here, where we have it shown as just in terms of sine and cosine. And then maybe I went for a common denominator, so I times the top and bottom of this by sine x, so I was able to write it all as one fraction. Lovely. Once I did that, I couldn't help myself. I wanted to factor. I saw those cos x's in there. And I also saw a negative I could take out. Didn't have to. And here's another correct version of the answer. All these are fine, but just be aware that if it looks like this in the back of the book, and you've got something that involves cosecant and cotangent, you may still be right, just written in a different form, and that's fine. The next thing we're going to look at is just some nitpicking on how to make your life easier when differentiating trig functions. So when you run into situations where they don't have to be this hard, you don't make them this hard. So far, all these different trig identities have been causing us grief. They've been giving us a lot of different ways that we could represent an answer, and it kind of makes us angry because we're trying to decide, well, what is the best way? And often that's a matter of taste. But there are times when the trig identities can actually save you a lot of work. So in general, look for opportunities to simplify before differentiating, especially if you run into something rough. Like this expression right here. It's a quotient, but the top of it has its own product. So you'd have to go off to the side and deal with this product, even to find the u prime of the top of this. And then you'd have your u prime and your v, and you'd have a big mess to deal with. And I've put that kind of solution into the PDF notes that are in the video description below. But let's look at a slicker way. Sine x, cotangent x is just cosine x over sine x, and this is all over cos x. Now when I look at that, I think sine x times cos x over sine x, oh, those are going to divide out. If I'm having trouble conceptualizing that, maybe I'll think this is a little on top, sine x over 1. Oh yeah, time for the red marker. These guys are gone. Nice. Now notice this is still y equals. I have not differentiated. I'm looking for opportunities to do stuff before I differentiate. So now I've got cos x over cos x. Hey, I could use my quotient rule now and it would be easier. But what would be better than that is to recognize that this whole function to begin with was just y equals 1 wherever it's defined. And now differentiating it could not be easier. The derivative of any constant is 0. And we're done. Like I said, if you want to see a more difficult way to do it, check out the PDF. But we'll do one more where there's an opportunity to make your life easier before differentiating. All right, here comes our last example of the day. So we've got a function that just looks like absolute misery. It's two quotients that each have a product in them. Honestly, if I got this and I didn't have any other techniques, I'd probably just walk away. And I didn't bother in the PDF of the answers to show an alternate approach to solving this. You can, if you want, to deal with it as is. But I'm going to look for something that will hopefully give me some insight to make it easier. So I've got x squared sine x over cosecant x. The only thing I can think of is the same sort of things I might have for trig identities. One approach you can take is to bring everything down to sine and cosine. So cosecant x is 1 over sine x. Secant x is 1 over cos x. Does that look better yet? No, not yet. But if we're going to divide fractions, we just flip and multiply. And again, notice this is still just y equals. I haven't differentiated. So I'm going to flip and multiply. This is times sine x over 1. The next one, I'll flip and multiply. Cos x over 1. So that's x squared by sine squared x plus x squared by cos squared x. I would argue that at this point it's actually a little less rough. Not a whole lot. At least we don't have fractions anymore. But it would be nice to put it in an even more pleasant form from here. And what you might notice is that you can do another common algebraic function or algebraic operation. You can factor. So x squared can come out. And that's going to leave us with sine squared plus cos squared. And the gag here is that sine squared plus cos squared is just 1. So y equals x squared times 1. Or y equals x squared. Now, that's not the answer to the question. The question asks you to differentiate, but that is a way easier to deal with term than what we started out with. Okay? So trig identities and being able to work with trig functions is going to help us put things in more pleasant forms. Once we get this, no big deal. It's not even trig anymore. There's our derivative. So the big ideas of this section are that we can differentiate any of our 6 trig functions. We've got to use them in conjunction with product and quotient rules where appropriate. And our answers might take different forms than are necessarily in the answer key, and they still might be right, and that's okay. Any correct version of the answer is fantastic. The other thing we got from this is that you should look for opportunities to simplify before differentiating, and that's especially true if something looks really, really rough. There's probably some sort of trick that you can incorporate in there. So I've got some practice questions for you. They're both on Schoology and they're in the video description below. Give those a shot, and then in the very near future there'll be a formative quiz on Schoology. It's not for marks, and there'll also be a quick little recap of what we've talked about this week in terms of trig differentiation.